Yes, sir.
Okay. Uh, okay. So welcome again for today's class, which will be the continuation of our previous discussion on photochemistry, particularly the reactions of organic molecules under photochemical reaction condition. Uh, as you know, in the last class, what we have tried to discuss was the Norrish reaction, okay? And we tried to understand the Norrish type 1 reaction, and that we have seen uh, that particular reaction, it has two steps in a broader way to say. One is the primary step or primary process, that is the irradiation, which leads to the excitation of the molecule from its ground state, singlet state, to the excited singlet state. And based on the position of its triplet energy states, the molecule undergoes the intersystem crossing. And then you have the alpha cleavage, or the cleavage of the carbon-carbon bond between the carbonyl carbon and the alpha carbon. Okay, that was the primary step, and after that you have seen the secondary steps, uh, which are in many ways. Sometimes you see the decarbonylation based on uh, if your another uh, alpha bond in the opposite direction, if that one is producing stable radical, so the decarbonylation steps will be predominating. In other way, you have the reactions based on hydrogen abstractions, and now uh, you will see the hydrogen abstraction sometimes from alkyl radical is going to abstract the hydrogen. Sometimes you will see from the hydrogen abstraction uh, by the acyl radical. Okay, and the third one was the definitely in any radical reaction, the recombination reaction that we have seen in the last class. And based on that, we have tried to discuss a bit of different examples. Okay, and today what we will do is we'll try to see the reactions based on beta cleavage. Okay, so you have seen the alpha cleavage. Now we are going to see the beta cleavage, carbon alpha and carbon beta bond. They will be undergoing the cleavage process. Okay, and then we'll look into quickly the Norris type 2, which is mainly the hydrogen abstractions by the biradical, I mean the oxygen based radical, and it will undergo by a 6-membered cyclic transition state to produce the different products. Okay, so that we will be looking at, and finally we'll be going through the photo reduction. This part in I mean all of this chemistry I have summarized in the maybe in the first lecture in a very short way, but now what we'll do, we'll try to elaborate these parts. Okay, so let us begin with the beta cleavage. Okay, so beta cleavage reaction. Some class of compounds have already weak alpha beta bond. Okay, weak alpha beta bond, which can undergo cleavage process. Okay, what happened to it? It is not working. just a minute. I don't know what is happening to the pen today. Oh, yes. So the condition is you have to have alpha beta bonds which will be weaker. Um, as a result of electronic excitation of the carbonyl compound, what will happen, the molecule will have cyclopropyl ketonic structure. Okay, so remember the beta cleavage will be predominating if you have cyclopropyl ring in the molecule. Okay, uh, and the evidence for the interactions between the carbonyl and cyclopropyl groups, which provides a mechanism by which energy may be transferred from the carbonyl group to the bond which is broken, is found in the UV-B spectrum. Okay, so the informations can be obtained by UV-B spectrum of the molecule where it is absorbing. Okay, that is important. Now, just let us come to the reactions, then it will be more clear. So, if you look at here cyclopropyl ring and you have a carbonyl compound, right? So, cyclopropyl ring is here, you have carbonyl compound. Now, this is your alpha carbon and this is the beta or this is the beta. Okay. So, after excitation, what is happening? The alpha beta bond is being cleaved. Okay. So, whether you are cleaving this one or this one, it doesn't matter, it is the same thing. So here you have the cleavage happening, okay, and you have two radical formation. Now after that, what can happen is the hydrogen atom shifting is happening either from here to here or from here to this radical. Okay, so 1 to hydrogen shift is happening, and you have, since you have both sides, you have a chance. So you have if you look at here, this, if the hydrogen is shifted to this side, alpha carbon, so you have a radical left here, right? And that radical and this radical is going to make one bond. Okay, and you have similar way, if it is shifting to beta, you have the radical left over here and you have a bond formation here. So in one case, what is happening, your CC bond formation is happening in between, and in another case the CC bond formation is happening at the terminal position. Okay, now in this case your hydrogen 1 to hydride shift is happening from here. You can, maybe you can write, this is, I wrote the wrong maybe, so this is A and this will be B. Okay, so in the B case, what is happening, hydrogen is shifted from this middle carbon to this beta carbon. Okay, so you have a radical left here and you have a double bond, so this is the product, and in the opposite case you have, this is the product. Now you see you have generated two alkene in this situation, and one alkene is more substituted than another. And not only that, this alkene is the conjugated. Okay, so you have alpha beta unsaturated keto, so that will be more stable, more stable. Okay, this is less stable, so your formation will be more, this will be more forming. Okay, so you have more substituted alkene and you have alpha beta unsaturated alkene, so that product will be major product. Okay, this is the minor, so less minor product. Now this is the chemistry. What is the chemistry? You have, the molecule should have one cyclopropane ring. Okay, and the cyclopropane should be where one of the arm of the cyclopropane must be the alpha beta bond with respect to the carbonyl carbon, okay, or carbonyl functionality. So that is the major part to remember. So what happens, you have the alpha beta bond cleavage, you have two radical formations, then you have 1 to hydrogen atom shift, okay, and then you have alkene generation. Okay, more substituted alkene will be more stable. So this is the thing you have to remember. Now let us look at this as example. Okay, so here also you have a cyclopropane, which one of the arm of the cyclopropane is the alpha beta, though you have the two arms here. Now what we see is that if you try to break this one, your ring is going to expand. So you are having five, 6 member to 7 member. Now 6 member to going 7 member is not that much preferable. Rather, if you have other bond cleavage, you can preserve the 6 member ring, and that is happening here. So you have this bond is being cleaved, not this bond. Okay, this bond is not being cleaved, though it is alpha beta 2, because you have if that is happening, your ring is going to be expanding from 6 to 7. So that is not that much preferable. So what we see is that here in this case, after bond cleavage, you have two radical formation. This is one radical and this is another radical. Now you have hydrogen abstractions. Now in this case, this hydrogen can shift from here to here, or it can be shift from here to here. Okay, now where it is going to shift, let us look at. Okay, so it is shifting from here to here, generating one radical here, and that two radical are making one bond, and you have now alpha beta unsaturated more substituted alkene formation. So this is the major product. Another product you can write, but that will be too little. So you have the formation of this CH2. Okay, so this is minor. This is minor, very less, but this is much more in concentration will be formed. So let us look at one more example. Now in this case, what we see is here, as I'm telling, this is the another route. So if you are cleaving this one, you are having 7 membered ring. Okay, and now you can have the hydrogen abstraction, I mean the hydrogen atom transfer from one to. So if it is transferred from here to here, what you are having, so you have one to hydrogen atom shift, and you have one is this product, another is this product. So among all of them, what will be the major one? You have this is the major. Okay, and 7 member ring will be the minor steps, and you have, if it is happening, the products will be among these two. This one here you have, if you actually try to uh, arrange them according to the stability or yield, what you'll have, you have the, this is maximum, and uh, then you have this ring formation. So these are all little amount. So if it is 50%, then other altogether will be 50%. Among them, this may be like 30, this is maybe 10 and 10. Okay, so like that it will be distributed. But you should know all these steps to explain the different distributions of the product. Now let us look at another interesting example. Here, if you look at what you are seeing, your product formation is this as the major one. It's very obvious because you have cyclopropyl ring here, cyclopropane ring. And in this case, this breaking is very diminishing, because you have, if you break this bond, you are generating a radical here which is much more stable. Okay, so what you have here after excitation, you can expect the formation of this radical. Okay, this biradical formation, got it? So now this radical is much more stable. Okay, so that's why this step is more predominating. And then you have hydrogen abstraction, and I mean the hydrogen shift, and you have generation alpha beta unsaturated ketone. Now if you look at to the opposite direction, what you have here alpha beta, I mean the alpha carbon and this carbonyl carbon, that bond or alpha cleavage can happen because you have here the secondary radical generation is possible. In the previous case, that reaction was not at all being seen, because the radical which you are expecting by alpha cleavage is not stable radical. Okay, so that's why in this case particularly, if I go for this example, third one, what we can see, you have the alpha cleavage product too. Okay, so if you do the alpha cleavage radical here, you have this radical. Now it can abstract the hydrogen and generate the unsaturation. Okay, so that is happening here. Now what is your job to find out what could be the real mechanism of this one, how the two double bond is coming here and a product is forming. So that one you can practice and try to find out, but the product will be based on alpha cleavage. That is the hint I'm giving. Okay, so
Sir,
yes, tell.
sir, middle one is a hydride shift or a radical. This hydrogen and this radical is formation bond, double bond formation, sir.
Which one you're talking about? The third
Middle.
example, this example.
Yes, sir.
Okay, this example, which what I'm telling here, you have this hydrogen, right? This
Yes,
hydrogen is
sir.
there. Up, so this your bond is cleaving this one, not this one, right?
Yes,
So
sir.
it is cleaving these
Mm.
radicals are forming. Now what can happen? This is the Norris type 2. So two hydrogen atom shift. Okay. So this hydrogen
Yes,
atom is
sir.
going to shift here. So you will have here hydrogen atom, and here you will have a radical generation, right? And you have
Yes, sir.
initially radical here, so that two radical will make one bond. Got it?
Okay,
So
sir.
yes.
Yes, sir.
Okay, now this one is coming from alpha cleavage.
Yes, sir.
Okay.
Okay, sir.
Okay. And now what you do is you try to find out what could be the mechanism of getting exactly this as the product. Okay, that is the practice one. You can try how it is forming, but it will be via alpha cleavage. Okay, so let us look at another complicated example. Now, when you have the structure like this, immediately you should look at whether the molecule is having any cyclopropane ring. Okay. Now, if you look at here, you have a cyclopropane ring here inside, right? Inside, and you have a five-membered ring, and the outside you have a six-membered ring, and in between you have the cyclopropane ring. Okay, so definitely this molecule is going to undergo alpha beta bond cleavage. Okay, alpha beta bond cleavage. How it is happening? This is via Norris type 2. So this bond is going to break because that will expand the ring from 5-member to 6-member. Okay, so this is your 6-member ring formation. And if this is breaking, you have a radical here, you have a radical here, right? So let me, okay, this is another example. Let me give you. So this is going to make one radical here, one radical here. Now after that, what can happen? This methyl can migrate here. Okay, you have a radical here, so you can migrate, generate one radical, and then you have a double bond formation. Okay, so that is happening. In the Norris type 2, generally you have seen the hydrogen atom shift, but here what we see is that methyl is shifting. Okay, methyl is shifting the position, and it is generating the more conjugated uh, alkene and the keto. Okay, so you have one, two for the conjugation. Okay, so that's why it will be much more stable. Now look at this as your example. Okay, this is you have alpha beta, or this is beta. So one of the alpha beta bond will be cleaved. Okay, so you can cleave this one. If you are cleaving, what you are having, you have this as your uh, so you have this other two radicals. Now what can happen after that? You have a hydrogen atom transfer 1 2. Okay, so if you are transferring from here to here, what is going to happen? You have this unsaturation. Okay, and if you are transferring from here to here, what is happening? You have in between the unsaturation, that will be more stable. Okay, so you have this as your product in this case. Got it? So if it is transferring here, you have a radical generation here, and that two radical are making the bond. So this will be your product. Don't forget to put this in. Okay, now you came to know that if there is cyclopropane ring and it has one bond which is as the beta bond of the carbonyl group, then you will have Norris type 2 reaction. Now it is not only the cyclopropane, even if you have the epoxide at that position, you will have the reaction. Remember here what is going to happen, you have the uh, C alpha and oxygen bond is going to be cleavage. So that is the difference what we have seen for, because you have here the competitiveness, you have alpha and oxygen, here alpha and carbon beta. Okay, but it is this bond is being seen to be cleaved. Okay, the product distribution shows like that, and you have these two radical formation, then you have the rearrangement. So the methyl here is migrating over here, generating more stable radical, and then you have double bond formation. Okay, so you have one three dicarbonyl compound is forming. Look at this one. You have this is the alpha carbon, this is oxygen, and this is beta carbon. So which bond is going to be cleaved? This bond is going to be cleaved, and you have this generation. After that, what is going to happen? The methyl is going to migrate, and you have this radical here, and then that will be making the keto. So you have 1 2 3 1 3 diketo compound is forming. Okay, so this is the way we look at how the beta cleavage product can be formed. Okay, the condition is you should have the substrate having a cyclopropyl ring or one epoxide uh, nearby. Okay, so let us look at Norris type 2. Norris type 2 uh, is a reaction, the photochemical intramolecular hydrogen abstractions. Okay, now what hydrogen? It is the gamma hydrogen atom. Okay, at 3 positions removed from the carbonyl group. Uh, by the excitation, carbonyl compound to produce 1,4 biradical, 1,4 biradical as the primary photoproduct. Okay, 1,4 biradical. Now, excited carbonyl compounds having an accessible hydrogen atom in the gamma position undergo characteristic 1,5 hydrogen abstraction or hydrogen atom transfer by an intramolecular cyclic process, 6-member transition state with the formation of ketyl like 1,4 diradical. Okay, let us look at how it happens. I think you are familiar with this chemistry when we have discussed the mass spectrometry. Okay, then there you have seen the hydrogen abstractions, right? Excited, I mean the electron bombardment, and you have the uh, radical coming out, and you have seen the by a 6-member transition state it can do that type of reactions. So that is happening here. What is the difference here? You have the biradical formation at the initial stage by n to pi star transition, and then going to singlet or the triplet transition state, followed by the hydrogen abstraction. So you have the radical here, you have hydrogen here. So that radical is going to take this hydrogen, which is generating this as your radical. Okay. Now, when you have this radical, it can do different types of reactions. Okay. Uh, what it can do, depending on the conformation of the initially formed 1,4 diradical, two different pathways are okay, is the actual process we see. Um, Number one, if only the orbitals of the radical centers can overlap, okay, a cyclobutanol product will be forming. That means if this uh, orbital, okay, having the radical and this orbital having the radical, okay, if they can overlap, you have the cyclobutane ring will be forming, having one alcohol group here, so cyclobutanol will be the product. Okay, so that is one thing. Second is, if the orbitals of the radical centers are parallel to the beta bond, they participate in the formation of two double bonds, one in the enol and one in the alkene, and as a result of cleavage of the beta bonds. Okay, so let us look at what does it mean with examples. So this is the one molecule you are exciting. So you have irradiated, and what it is going to make, you are having this as the products. Okay, these as the products. How it is happening? How it is happening? Uh, how it is happening? So you have immediately, you should count alpha, beta, gamma. Okay, alpha, beta, gamma. So you have gamma bond here. I mean gamma hydrogen. So you can have 1, 2, 3, 4, 5, and hydrogen 6. So 6-member transition state. Okay, that will make initial biradical as this one, this carbon radical, you have OH, and then you have another carbon having R1 and here R2, then you have CH2 and CH2 radical. Okay, now after that, what can happen? This can undergo bond cleavage. So okay, you can have this radical generation, which will ultimately generate this RCOH, C, this R1, R2. Now this will make a double bond. Okay, got it? So it is I mean enol. So you have in and all, enol formation here. Now enol can undergo tautomerization to give you the keto. Okay, so that will be happening. So C, you have R1, R2, and hydrogen. Okay, so this is this product. Uh, Sidewise, you have this alkene is coming out. So you have alkene, CH2, CH2. Now this is completely different one, where you see the initial biradical formed, they recombine to give you the cyclobutanol. Okay, so initial biradical was a carbon, you have OH, this radical. Now you have another carbon, you have two R1 and R2, and you have CH2, and you have another CH2 radical here. So that is going to make the bond, and you are having the cyclobutanol. Okay, so these are the way how it is being formed. Now if you look at this substrate, what are the products you are expecting? You have the gamma here, carbon, so you can have gamma hydrogen abstractions, and this alkene, I mean enol, and this carbonyl compound, I mean this substituted alkene. Now enol can undergo tautomerization to give you the acetophenone here. So you have AR C double bond O CH3. Okay, so this is going to be your product. Now here a couple of examples I'm giving what could be the possible product for this substrate if you irradiate under uh, light, UV light. So what is going to happen here? I'm giving the product. So this is going to be the product. Your job is try to find out how it is happening. Okay, what is the mechanism by which it is happening? It is Norris type 1 or Norris type 2. Okay, that you have to find out. Now couple of other examples. So here I'm giving one more example. uh, this one you need to find out what okay, the product I'm giving here also, this is going to be the product and how it is forming. Okay, the third one, let me tell you, suppose you are given with this as your substrate. Okay, so you have alpha, beta, gamma. Okay, so initially the gamma hydrogen abstractions is going to happen. That will generate the biradical. So if it is happening abstracting from here, so you have a radical here and you have a radical here, that two can combine. Now here in this case, the elimination reaction is not happening. Okay, what I'm telling is after, so your generation of this radical, okay, this hydrogen and this carbon with this radical, and this radical happens. Now after that, what you have seen, you can have the alkene formation. Okay, so if that is happening, your alkene formation will be like this. Okay, so you have a radical here. uh, Let me write here also. So you will have two radicals, and this is going to be coming out with this radical and this radical, right? And ultimately you are expecting this ketone and this alkene, enol. So enol is going to be rearranged, tautomerized to produce the this your ketone. Now this is happening because you have the double bond formation at the bridged position, which is not preferable. Okay, so that's why this step is completely diminishing, and you have only the recombination of the biradical formed uh, after gamma hydrogen abstractions will be the major product. Okay, so now many people have the question, sir, I have here, I can think about the alpha cleavage. Okay, so you do think about the alpha cleavage. You can have the alpha cleavage, but that is your minor product because you have the generation of only primary radical, which is not that much stable. Okay, so that's why the gamma hydrogen abstraction is the major route where you are having the generation of, see, I mean the more stable radical. Not only that, you have the process is happening a six-member transition state, which is more preferable. Okay, so that's how you will see the selectivity of the reactions. Though you have different routes of having product formation, but you have only in this case this as your major product. Okay, so that way we are I mean getting the single product here. So you should explain how it is happening in this case and in this case. Okay, so I'm left with very little part, which is photo reduction. Now, in the regular reduction process, what it tells is either you are having the hydrogen addition, or the process is gaining the electrons. Okay, so it is somehow getting the electrons from other substrates or reagents. Okay, that you know as the reduction. Now here the particularly in this situation, photoreduction are of two types in this case. In one case, okay, sorry for this uh, this cut off. Okay, so let us go to the topic. What I was talking about the reduction. So I was telling that in photo reduction of the carbonyl compounds, uh, it is of two types. One is you'll see the product which is going to have the hydrogen addition, and in another way you will find the product which will be gaining the electrons. Okay, now what is actually your substrates, uh, or what are your substrates undergoing the reaction that matters in this case. Okay, now let us look at this first example here. What we find is you have the benzophenol given. Okay, and this is another substrate which is having the reduced form of the benzophenol. Okay, so if you do reduction, regular reduction, what you will have, this carbonyl compound is going to make the keto. So sorry, this keto is going to make the alcohol, secondary alcohol. So this is the secondary alcohol. So what you have done here, you have mixed these two, and you try to do the photolysis, and you came to know that if you do photolysis, so you have excitation, singlet state will be achieved, then it will go to the triplet state, particularly for this benzophenol. And what you will see here is that the biradical formation, and then you have a hydrogen abstraction. Okay, uh, okay, I had some couple of other examples too there in the previous case. So it will be there. You just need to look at what will be the major product in the previous discussion. Okay, so I'm not going back to that one. Let us look at how it happens. Okay, so you have singlet excited state, then triplet. Now you have the alcohol. Okay, now you have the alcohol. What is going to happen? So this means you have two radical generation here, but the triplet means you have two same directional. Okay, now this oxygen and carbon, two radical. So which radical is more reactive? Which radical is more reactive? Your carbon
Oxygen
center
radical.
oxygen radical is more reactive. So that is going to abstract the hydrogen. Okay. Now that is going to abstract the hydrogen from this alcohol. Which hydrogen it will abstract? It will abstract this hydrogen, alcoholic hydrogen, or this carbon hydrogen. Which hydrogen it will abstract? So this is generating, I'm just writing in this way, C radical, oxygen radical. Okay. And you have this pH2CH OH. Okay, it's reacting. So which radical, oxygen radical, is more reactive, as you told? So it is going to react. Now you have two hydrogen available. One is carbon center, one is oxygen center. So this oxygen is going to take which hydrogen?
Carbon center.
No,
Carbon center hydrogen.
no. It will take which center hydrogen? It will take the hydrogen uh, from a center which will produce more stable radical. Got it? So what you are having here, uh, okay, so no, you are right. So what you are having, yes. So it should take the hydrogen from a center which will produce more stable radical. So that's why it will take from the carbon. You're right. So you take from the carbon this hydrogen, so to produce this radical. Okay, so pH to C radical OH. Okay, now this radical, they will recombine two of them to generate pinochle type of product. So here if I write, two of them will be uh, coupling. So you have OH, this radical, you have COH, pH2, this radical. So they are going to couple to give you the diol. Okay, so you have diol formation. 1 2 diol, pH, you have pH, here you have pH. Okay, so diol formation is happening in this case. Now this reaction is actually telling you the reduction is here based on hydrogen atom abstraction. So your initial compound have whatever hydrogen, at the end what you are seeing, hydrogen has increased to that substrate. Okay, so you have two OH here. Initially, you have this as your substrate. Okay. Now, in your first semester or second semester, I have told you you can verify the oxidation state of the central carbon and find out how many electron transfer apparently has happened in this process. Okay. If you just look at the substrate and the product. Okay, so your substrate here, you have one oxygen connection and two carbon connection. Okay, so your carbon will have, what is uh, the charge apparently looking, you can see, look at here, if you consider the oxygen, so your oxygen gives 2 minus, so you have a carbon here 2 plus. Okay, then it will be negative, I mean the neutral overall. And if you look at the substrate here, you have one oxygen connection, okay, at this center. So you have one oxygen connection with single bond, so you have oxygen OH will be -1, so you have carbon +1. Okay, so in one center you have one electron transfer process in one center if you consider, but you have two centers they are undergoing the reactions. So two of them, okay, and here overall you have charge is +1 +1. Here overall charge is +4 if you consider two. So ultimately, two electrons has been transferred. Okay, so this is undergoing the reduction process. Now look at another kind of reactions where you are having an external additives which can provide the hydrogen. Okay, in the previous case you have seen the same alcohol, the corresponding alcohol you have utilized as the hydrogen donor, but here you see your hydrogen donor is cyclohexene. Okay, because you have the cyclohexene having two allylic hydrogen that are I mean very labile, it can easily be donated, okay, as hydrogen atom. So in this case, if you take the acetone and do the hydrolysis in presence of cyclohexene, what you will see initially, that is going to happen. So you have this radical carbon center here, this radical formation. And after that, you have multiple products you can observe based on the probabilities. Uh, one is you will have this allylic radical, it can undergo self condensation, I mean self recombination. So that is giving to give you this as the product. You have another option is that this carbon and this carbon radical, they can combine. So to give you this as alcoholic product. Another option is that you can have the hydrogen abstractions further, okay, from this substrate. So you can have another allylic position, so it can take this hydrogen to generate this radical. In this case, you'll have this one, and simultaneously you will have this radical, which is ultimately you have uh, this is going to be your another uh, product. So you have multiple product formations. That's why generally to minimize the probabilities of multiple variations, we do the use of, I mean, we use the corresponding alcohol as the hydrogen donor, okay, to have better reaction. So in this case, if you do the propanol, okay, you will not have that type of variations. Rather, what you have seen in the last example, you will have the product formation, which will be the 1,2 biradical, 1,2 hydroxy compound will be formed as this one, pinnacle. Okay. Um, Now let us look at the how electron transfer process happens. Say suppose you have naphthalene, okay, and naphthalene you have a lot of low pi star energy levels, okay. So if you give suitable donor of electrons, okay, sacrificial electron donor, here you see you have R3N amine trisubstituted, okay, 3-degree amine. So these radicals can easily be donated. Okay. So if you do excitation, this naphthalene, it can take one electron from this radical, electron donor, and you will have the initial formation of this radical anion, and this radical anion can abstract the one hydrogen, okay, a cation, to generate this radical. Okay, so you can think in this way. You have uh, this radical anion, you can write in this way. So you have negative, you have dot, okay, and this negative can take one hydrogen plus. If you talk about the triethylamine, if you look at triethylamine, okay, so N, you have one ethyl. So you are donating one electron, so you have dot plus here, and you have hydrogen here. So what can happen? This anion can take this hydrogen and generate one negative here, okay? And this negative and this plus can make a double bond. So here that hydrogen, if it is taking, you have this situation, your radical is here, which is stabilized, so it can generate more stable form. Here, this radical can migrate. And again, you can have two types of reaction. Either it can abstract the hydrogen radical or hydrogen electron. It can gain from another molecule of the substrate, okay, the sacrificial electron donor, and you can have followed by hydrogen cation, okay, H plus addition to give you this reduced form, okay, or you can have the recombination of these two radical to generate this dimeric compound, okay. Ultimately, you have the electron transfer followed by H plus addition, and you are having the reduced product. Similarly, you have here another example. If you look at, you have the cyano compound, and if you use the borohydride, cyano cannot be reduced by borohydride. What happens here? The ring will be reduced, okay, and you have this product formation. How it happens? You have excitation, then you have borohydride here. So borohydride here, how it is working? It is working as the hydrogen atom donor. Atom donor. Rather, not being used as a hydride transferring reagent. Rather, it is being used as a hydrogen atom donor, and you have the, the hydrogen atom abstractions from borohydride, and you have anion here, which is stabilized, okay, and it is generating the most stable anion. So it is here. Now it can be quenched if you are using the protonating solvent like you have here water. Okay, so ultimately you have this as your product. Okay, so these three different types of example we have seen today. The reduction without adding any kind of so-called reducing reagent, rather the carbonyl compound and its corresponding alcohol can be used as a carbonyl compound reduction can be obtained by using the corresponding alcohol compound, which will be donating the hydrogen, and that process will give you the major product as the 1,2 hydroxy compound. And if you use the other electron donor, you will have the products formation, but based on the hydrogen donor, what will be your major product that will be driven. And if you have the other kind of the sacrificial donor, if you have the more electron rich system like alkane. So substituted alkane, they can be used as the electron donor, and you can reduce the naphthalene kind of substrate which has low lying pi star orbitals. Okay, so can easily accommodate the electron, and the reduction process can be seen. Okay, so these are overall different reactions. Today's discussion I did. What we are left with is you have just two to three different types. What is one is the dipymethane and rearrangement. Another is you have the Barton reaction. We'll just have the recapitulation of the Barton reaction in the next class. Dipymethane I will discuss a bit, and you have the chemistry of arenes. Okay, so yeah, that's all. Maybe I'll just take one more class in the coming days, and I'll try to finish as early as possible. If you have any queries, you can do ask today, or when you are coming, you can try to clear your doubts in the coming days. Okay, so do you have anything to ask? Anything you want to ask? If you don't,
Sir,
yes.
sir, R3 and radical this hydrogen F plus then this ethyl and dot plus and hydride and M methyl form, sir.
Which one you are talking? This one you are talking?
This one. Yes, sir. Yes.
Okay, so what is your question here?
Then R3 and dot this ethyl 2 and dot plus and hydride and methyl. This one is formation. How to form this?
No, no, this is one example. R3 means you have three alkyl. So you are this is the general example of the sacrificial amine. So it is tri-substituted
Yes, sir.
amine. Okay, NH3 is the ammonia. You have, if you replace H with R, suppose ethyl. Okay,
Hmm.
so you are having triethylamine, right? This is the actual example I'm talking. This is the general sacrificial amine. This is the example actual substrate. So if you are using the triethylamine, how the reaction will happen, that is I'm going to explain here. I'm trying to explain. So
Yes.
triethylamine means you have three ethyl. So the N, okay, this is one ethyl, you have another ethyl, you have another ethyl. Okay, now here you have two hydrogen, right? You have CH2 Me, right? Now what I'm telling is you have nitrogen two radicals, right? One lone pair. Two radical means
Yes,
you
sir.
have one lone pair, and not radical. You have lone pair of electrons. So when the your naphthalene is excited. Okay, so when it will come to its like first excited state S1, there it can undergo the electron transfer process. Okay, so naphthalene, since it is having pi star, energy is quite low, so it can easily take the electron to be quenched. So this n, I mean this lone pair, it can donate the electron to the pi star of this naphthalene at the excited state, and naphthalene will be dot minus because it is gaining one electron, and this triethylamine will be dot plus because it has lost its electron, one electron. Okay, then you have since naphthalene have dot minus, so that can be quickly rearranged as this is minus and this is dot. Okay, so naphthalene can be rearranged to this situation. So you have a minus and dot. Okay, this situation, and this minus can abstract the proton from this triethylamine, and if it is taking this proton, what do you have? You have here uh, minus, right?
Yes, sir.
Yeah. So sorry, this is what I have written. Yeah. So you have this minus formation. Okay. So this N now is triethylamine after donation of electron. What you have dot plus, and then it is giving up one proton. So you have a minus here. So minus and dot plus can make a double bond. So you have N double bond this, and this will be your fate of the donor, and your naphthalene will be finally converted to this radical, which can another I mean the electron can gain and proton can be abstracted from another molecule of triethylamine and generate this reduced form, or it can undergo dimerization process. Okay, so two of them can be recombined. So that is the way it does the reaction.
Okay, sir.
Okay, so
Thank
yeah, that's fine. So if you have any further queries, just revise the whatever I have taught and try to clarify when you are coming in the campus. Okay, so thanks for attending today's class. I'll be sharing this in the group. Okay, my classroom. So stopping here.